This talk is about question 36 of your assessment task about steels. You need to detail 3 types of steels, what their properties are, what their alloying elements are, and what they're used for. And the 3 types I've recommended you look at are carbon steel, stainless steel, and something called HSLA, which is high strength low alloy steel. The first one, carbon steel, you need to define what carbon steel is. Carbon steel is iron with a certain percentage range of carbon, and you need to detail what that percentage range is. It can have some other elements inside and still be called carbon steel, and therefore you need to detail which of those elements you can have in carbon steel, what percentages you're allowed to have in them and still be called carbon steel, and why they are added. Now, within carbon steel, it's usually broken up into 3 different categories. You've got the steels with very low carbon, the steels with high carbon, and the steels with moderate carbon. They've got names. So for each of those 3 types, what are they called? What are their properties? And what are their uses? And as part of that, in general, you should detail how does steel properties in general change as you increase the carbon percentage. So what happens to steel as you increase carbon percentage? The next type of steel is stainless steel. It's an alloy of iron, chromium, nickel, and sometimes something else. And the main thing you've got to talk about with stainless steel is particularly why we use chromium. What does the chromium do for the stainless steel? It makes it stainless, so you've got to talk about that in detail. It's very important. What percentage chromium do you need? But you've also got to mention, why do we add the nickel? As for the chromium's doing a lot of the corrosion protection work, what's the nickel for? And lastly, what's this other element they sometimes add, particularly for use in ocean environments? So where do we use stainless steel and why, based on the properties of stainless steel? Next, you've got HSLA steel, which is high strength low alloy steel. You need to say why it's got low percentages of carbon, why do they add manganese to the steel, and why do they add tiny amounts of titanium, niobium, and zirconium to this steel. And you need to talk about how those alloying elements give it its properties, what are its uses, and why do we use this HSLA steel. Now this talk's going to be a little bit longer because I want to go into a bit of detail into steels, because even though you've done this study, you might not fully understand why these alloying elements change steel's properties the way they do. So we're going to look at carbon steel first. If you take carbon steel and magnify it and zoom in with a microscope, you'll see that steel, like all metals, is made of grains, little individual crystals all squashed together. And if you zoom into one of those crystals of carbon steel, you'll see it's actually got this laminated structure. You see different layers, like all lined up in a row with each other. So it's called a laminated layered structure, and that structure is called perlite. And it consists of 2 phases, or 2 components of steel. And the first one is called ferrite, which I've drawn in the grey. And the ferrite phase, or the ferrite layers, are almost pure iron with a tiny amount of carbon atoms in between the iron atoms. So if you could zoom in and look at the individual atoms in ferrite, you'd see it's mainly just big iron atoms with a few carbon atoms scattered in between, and that's called the ferrite layer. But the other layers in between the ferrite are something called cementite. It's actually a compound that's made between iron and carbon, or Fe3C. And it's a very, very hard compound. So what you've got in normal carbon steel is each grain is made of this laminated like composite structure, where you've got strong and tough ferrite, it's not brittle at all, and you've also got very hard or very strong but brittle cementite in between. And combined, the fact that you've got this strong and tough ferrite and this very strong but brittle cementite actually means that steel has got a combination of all those properties. Steel is hard and strong and tough, and that's why we use steel for so many applications, because it's got such an incredible strength and good toughness, and it's also fairly common and also fairly cheap. But as you change the percentage of carbon in the steel, as you add more and more and more carbon, there's only so much carbon that can actually dissolve in the iron in this form of ferrite. And then if you start adding more and more carbon, what it means is you start to make more cementite. More of that carbon actually binds with the iron to make this cementite compound. And that means as you increase the carbon percentage, you increase this cementite percentage. That makes it stronger because cementite is very, very, very strong, but it's also brittle. So that's why steel's toughness goes down. They become more brittle as you increase the carbon, and it also increases the corrosion rates of the steel as well, because we know that the carbon impurities are important for the rusting process. On the other side, if you decrease the carbon, that means you decrease the amount of cementite you've got in there. It doesn't decrease the strength a bit, but it does make it more tough, and it also makes it more ductile. So that's why changing the carbon percentage changes the properties of steel. However, for HSLA steels, it's a little bit different again. For high strength low alloy steels, you use very, very low amounts of carbon, so you don't get cementite. So because you've got low carbon, you've got no cementite. But you do add these tiny amounts of other elements, such as titanium and niobium, and they actually react with the amount of carbon you've got in there. So what you end up with is ferrite, which actually has only a very, very small amount of carbon, because most of the carbon is now inside these things called carbide precipitates. Because the titanium, niobium, zirconium you add reacts with carbon to form these compounds of carbon, and they scatter throughout the whole structure. Rather than being those layers we saw before, we get these tiny spherical-like particles of carbides all throughout the steel. And these are strong, so they increase the strength of the steel, but because they're not in layers, they don't decrease the toughness. So what you've got now is steel that's got the strong carbides in there without reducing the toughness, and because all the carbon's been soaked up, most of the carbon's now trapped in these precipitates, you don't have all those carbon impurities in the steel which would cause corrosion. So HSLA steels, because of these tiny inclusions of these transition metals, you form the carbides, they strengthen the steel without decreasing the toughness, and they also soak up the carbon, which means you get lower corrosion rates for HSLA steel as well.